The answer is that you're on the moon. Now, there's many ways you can solve this question, but the one that I think is the most fun and probably the most useful is figuring out how range, the distance you can throw an object, scales with the acceleration on a planet. And what do I mean by that? I mean figuring out this proportionality. Is the range proportional to the acceleration on that planet? Is it proportional to the square? Is it proportional to something else? Let's see if we can find that out. So this has become a question of how does range scale with acceleration? And the reason why we're looking at proportionality sorts of arguments is because these two numbers, the range on Earth and the range on this unknown planet, how far we can throw these rocks, so we also know their ratio. And ratios are used whenever we have these proportionality sorts of arguments. Well, we already showed in the previous problem that the optimal range occurs at 45 degrees. So if we throw something with an initial velocity of v0, these are the horizontal and vertical components. Well, when we're calculating range, the first thing we want to know is how much time does the object spend in the air. And we think of measuring to the top of the trajectory and then multiplying by 2. How do we find the time it takes to get to the top? Well, we use this equation, we plug in our known values, and solve for t. Now you'll notice I haven't been using numbers. I've been keeping everything in terms of variables, except for this 45 degrees. This can be an intimidating tactic to use when you're first solving physics problems. Often you tend to want to plug everything in, but actually you can often get more interesting results if you leave the variables in place and don't plug in until the very, very end. Anyways, this is the time to the top of the trajectory, but we know the full time is twice that, so I'll just put a 2 here. Once we know the time, how do we find the range? Well, we use this equation. And now I've plugged in for the initial velocity, the initial x velocity, v0 cosine 45. I've multiplied by the time that we just calculated, because remember, in the x direction, the acceleration is always 0. Okay, let's simplify. Well, I've multiplied the v0s together to get this v0 squared, and actually if I carry out cosine 45 times sine 45, I find that's just equal to 1/2. This part, the 1/2, cancels with a 2. I find that my maximum range is equal to my initial velocity squared over a. Now, I don't really care about v0 squared. I want to know how range scales with a. And it turns out, well, it's proportional to 1 over a. Or, r is proportional to a to the negative 1. Well, so what? How do I use that? Just like we did earlier in the unit, we found that we can write a ratio. And the ratio of the range on Earth to the range on this unknown planet is going to be equal to the ratios of the accelerations, taken to the negative 1 power. Negative 1 power just means flip what you have inside. I can solve this for the unknown acceleration, and I get this equation. The acceleration on our unknown planet is equal to the ratios of the ranges times the acceleration on Earth. When I fill in what we know, I find that the acceleration on our unknown planet must be 1.6 meters per second squared, which is exactly the acceleration on the moon, and we've figured out where we are. Amazing work. There are other ways to solve this, equally valid, but this is one tool that you should try to familiarize yourself with.